Okay, now I'm recording this. When the atom vibrates, it's the atoms that are vibrating and bonds that are vibrating. So when this absorbs infrared radiation, which causes the vibrations are going to be based on having a trigonal pyramidal geometry. And that's going to vibrate differently than something that has a tetrahedral geometry. But the electrons aren't vibrating in that sense. The atoms would be. And so this is important here. All right, so this is what you're going to do. This is why I say don't use the report sheet, because I'm not following the report sheet. You're going to do these in your notebook, and you need lots of space to do these. Okay, the next thing I need to talk about, and this is for the next structure, are double bonds. When we have double bonds and triple bonds, then we have to consider these. We have to consider the PP pi bonds and something called a PD pi bond. And so when we have double bonds consist of 1 sigma and 1 pi, always. A triple consists of 1 sigma and 2 pi bonds. And so let's take a look at the next structure. What is the next structure? COCl2? Okay. And so if we do COCl2, we come up with a Lewis structure. It looks like this. It's trigonal planar because we have 3 groups of electrons with 3 bonded atoms. The first thing we do is we figure out the hybridization. What is the hybridization on carbon here? sp2. But we're also going to figure out the hybridization on the terminal atoms. Now, Petrucci doesn't hybridize the terminal atoms. But I'm going to have you hybridize the terminal atoms. We'll just hybridize all the atoms. The reason we're going to do that is it just makes things more consistent. Now, who's right? Is Petrucci right or am I right? Well, neither of us, because really what it is somewhere between. Well, maybe somewhere between. Actually, in this case, it's probably hybridized. So in certain cases, I would be more right. In other cases, Petrucci would be more right, because it depends on the atom size. Now, the repulsions, why do we hybridize? We hybridize to minimize repulsions. Now, the repulsions are going to be stronger for big atoms or small atoms. Repulsions are going to be stronger for small atoms because small atoms, things are more crowded. And so I would be more right for small atoms, but Petrucci would be more right for big atoms because you don't have to hybridize as much for big atoms because the repulsions aren't as great. When I'm talking about these hybridizations, we talked about SP. SP is 50% S. SP2 is 33 1/3% S. SP3 is 25% S. They don't just stop at those numbers, 50, 33 1/3, 25. What tends to happen is the hybridization goes in the amount that's required to minimize the repulsions. There's going to be a balance between the energy required for hybridization versus the energy to minimize the repulsions. And so typically when we do this, we look at what the bond angle is, and is the bond angle, depending on that tells us the percent hybridization rather than does it fit one of these categories of hybridization. And so a lot of people, when you're talking about this stuff, they'll talk about, what percent S or what percent P are in the bonds. And that tells us the degree of hybridization. Is it closer to sp2? Is it closer to sp3? Where is it? And so it's not quantized in that level. It's a continuous spectrum of hybridizations in which we go from unhybridized to fully hybridized. And so this is why I'm going to deviate from what Petrucci does, and we're going to hybridize all the atoms. And so if I hybridize all the atoms, what's the hybridization on oxygen here? This should be automatic. It should be automatic because you just count the groups. 2 groups, sp. 3 groups, sp2. 4 groups, sp3. How many groups of electrons on oxygen? 3. Lone pair, double bond. That's 3 groups. 3 groups is sp3. Oh, no, sp3 would be 4 groups. SPPP, that's 4 groups. SPP would be 3 groups, so it's sp2. It's sp2 hybridized, just like carbon. What about these chlorines here? What's the hybridization on chlorine? sp3. And both of these are sp3. Okay, now we're going to look at it atom by atom. And so first let's do the carbon. Carbon's sp2. And so you either just memorize this. We have 3 sp2 orbitals, which leaves 1 unhybridized p orbital on carbon. And then we fill this not according to valence electrons on the periodic table, not according to the number of electrons over there. We fill it according to, because if I look at the number of electrons, well, number of electrons in the Lewis structure, how many of these belong to carbon according to formal charge? I got 1, 2, 3, 4. This carbon has 4 electrons. It's supposed to have 4 electrons. It gives it a formal charge of 0, right? But if I were to fill these orbitals with 4 electrons, this is what I end up with. 1, 2, 3. The 4th electron, we pair it. Is that what I observe in the Lewis structure? No, we never fill these according to the number of electrons. We always fill these according to the Lewis structure. According to the Lewis structure, I don't have any lone pairs on carbon, do I? There are no lone pairs on carbon, so where does the 4th electron, where must it go? It's got to go in this P. There's no other way. It's got to go in the P. And so this is the way we can look at this. When I draw this out, I can draw it in 2 perspectives. Draw out the sp2, sp2, sp2 like this. The single electron, single electron, single electron. Now where's that p orbital? The p orbital is coming straight out. It's perpendicular to the board, so it's coming straight out and going straight in. And there's an electron in that p orbital. Here. That's the unhybridized p orbital. It's probably easier to see this as a side perspective. And so this is what I call looking from the top. If I look at a side view of this, what I'm going to do is I'm going to rotate this 90 degrees here. And so the carbon's going to be here. Now this sp2 is still in the plane here. But what's going to happen is this sp2 is going to stick out of the plane here. And so one of these sp2s, let's draw like this, sticks out, and another sp2 sticks in. And so I still have this trigonal planar arrangement, so I just grabbed it from this orbital and just twisted it this way. And so now this one's sticking out and this one's sticking in. These are going to have electrons like this. Well, what that's going to do is it's going to put the P in profile like this. And so this is just one p orbital and it has 1 electron like that. And so this is the top view, this is a side view. You have to be able to draw these. How about the oxygen? Let's take a look at the oxygen, because that's where the double bond's happening. When I look at oxygen, oxygen is sp2 hybridized. And that leaves 1 empty p orbital. Now I'm going to fill these according to the Lewis structure. What do I have? I have 2 lone pairs. And how many electrons does this oxygen have? 1, 2, 3, 4, 5, 6. It has 6 electrons. So 2 lone pairs, 4, 5, and 6. Just going to fill it like this. So I'm going to draw like this. Okay, here's my oxygen. I got sp2 hybridization, like this. Actually, oxygen is smaller than carbon. So I shouldn't draw bigger. Why is oxygen smaller than carbon? Yeah, Z effective is better. So those are my sp2. I got 2 lone pairs like this, 2 lone pairs. And then I have 1, but you know what? I'm going to flip these. Sorry. I need to flip these. It doesn't matter which way, spin up or spin down. These ones I'm going to spin down here. And so I'll put this oxygen spin down here in this sp2. So I got my 3 sp2 orbitals. Where's the p orbital? The p orbital is going to be like this, coming straight out. And this is going to be spin down. That's my p orbital here. What view is this? Is it a top view or side view? This is a top view. Let's draw this in profile. So what I'm going to do is I'm going to take it from this bottom one and spin it a little bit. And so from the side view, it's going to look like this. This one's still going to be here, like this. But I'm going to get 1 orbital coming out, like that. 1 orbital going in, like that. So this is going to be a lone pair coming out, like this. This will be a lone pair going in, like that. Then this one's just going to have 1 electron. And then the p orbital going to be here with 1 electron spin down. And so in valence bond theory, what we have is a bond consists of orbital overlap. And so let me erase this here right now and draw it. So let's draw the bond from the carbon to the oxygen. Okay, here we have one of the bonds. This is an sp2 on oxygen bonding to an sp2 on carbon. And so this is an sp2 sigma bond here. But if you look at what's happening with p orbitals, we have a p orbital on top here on oxygen and a p orbital down here on carbon. And even though they look far apart, when we look at the probability distributions, they can overlap above and below the plane. And so we have a p-p pi bond here. And so what a double bond consists of is it consists of a sigma bond here and a pi bond here. The pi bond, well, that's 2 bonds because we have 2 overlapping orbitals. This is looking from the top. And so let's look at the double bond from the side. Look at the double bond from the side. I still have my sp2 sigma like this. But now this orbital goes in and this orbital comes out. Those have a lone pair. This orbital is coming out. This orbital is going in. These have single electrons in them because they're going to bond to something else. And so here's my sp2 sigma. But now what I can see is I can see the pp pi bond in profile like this. And the way we represent a pp pi bond is we just show that these lobes will have overlapping electron density here, even though it looks far apart, but these aren't walls. These are just 90% probability boundaries. So there's going to be overlapping electron density here, like this. So a pp pi. It's my pi bond. It's my sigma bond. Okay, this interesting thing about sigma bonds. Sigma bonds, you can rotate the atoms without breaking the bond. And so across single bonds are freely rotating. They're free to rotate because nothing's going to upset the overlap. Whereas pi bonds are not free to rotate because if you rotate, let's say I rotate the oxygen, I'm going to break the pp pi bond, right? And so for pi bonds, you cannot rotate for sigma bonds, you can rotate. And so it fixes the shape sometimes, because a lot of these molecules are like spaghetti. You know, they rotate and they look like spaghetti when they're moving. But when you have a pi bond in there, they become rigid.
Can you show how you can rotate a sigma bond?
Yeah, I can show you how to rotate a sigma bond. Just a sec. Well, I'll do it when I get to the chlorine. When we look at this, though, is a double bond twice as strong as a single bond? And the answer is no, because the single bond, when you look at the electron density in the single bond's here, you know, right between the two nuclei. In the double bond, you know, the pi bonding electrons are going to be outside the internuclear axis. And so there's not a direct attraction to the two atoms. They're going to be attracted up and down, or left and right, here, as in this case. And so double bonds are stronger, but not twice as strong. All right, so the way we represent that double bond is like this. We have one oxygen coming in here. This one oxygen has an sp2 electron coming in here, and the same oxygen has a p electron coming in here. And so this oxygen is going to double bond to this carbon. Well, what about these other two bonds? What's happening with the other two bonds? The other two bonds, we're going to have chlorine come in and bond here and here. Well, the chlorines are going to be sp3 hybridized. And so let's take a look at the chlorines next here. And so when we look at the chlorine, we got 4 sp3 orbitals, and we fill it according to this. So chlorine has 7 electrons, 3 lone pairs. And so 7 electrons, 3 lone pairs, 1, 2, 3 lone pairs, and the 7th is going to be a single. And so when we look at this, I need to flip the spin on the chlorine. Sorry, I got to do that one more time, because it's got to bond to this carbon here, and here. And so what I'm going to have is I'm going to have a chlorine come in here and bond. Well, chlorine's sp3, and so sp3 we always draw the same. 2 in the plane at a tetrahedral angle. And then 1 coming out and 1 going in. And so 2 in the plane, 1 coming out. Well, these are going to have lone pairs in them. These 3 here. This is going to be dashed here. And this is going to be singly occupied. And so when I look at this, this is going to be an sp3, sp2 sigma bond here. Now, what I mean by free rotation is this. The chlorine can spin, so those lone pairs, you know, aren't fixed like this. The lone pairs are spinning around. And so this is like a propeller, you know, spinning. At room temperature, it's going to be spinning. It's not going to be static. But this oxygen is going to be static. These lone pairs are fixed. Here, those orbitals. Okay, and then we have another chlorine in here, coming in here. This is going to be sp3. This is an sp3, sp2 sigma bond again, here. And then 3 lone pairs. And so we do it the same. 2 in the plane, 1 coming out, and 1 going in. And so we have that. These are all sp3s. Here. And so here we have chlorine sp3 electron coming in here to bond here, and another chlorine sp3 bond here. Yeah, I'll try to code the chlorine electron a little differently. So I ran out of colors. So I don't need what colors. All right, and so here we have to put in the chlorines here. I didn't leave myself enough room, but you don't have to draw it super accurate for the chlorines because it's hard to. just show it like something like that. Any questions about this? All right, what's the next molecule on that chart?
SOCl2.
SOCl2. All right. SOCl2, this. Is this the Lewis structure you got? This one shows isomers. Do you know what isomers are? Isomers are the same formula, different structures. Both of these structures have zero formal charge. Both are okay. Or do they? Did I make a mistake here? Did this one have a lone pair in here?
Yeah.
This one has a lone pair? Like this?
Yeah.
Yeah? Oh, that complicates things. Because if this one didn't have a lone pair, it's just like that one. It's easy. But now this one has a lone pair, it really screws things up. Well, let's do the easy one first. Do you see this one's easy? You know why it's easy? Well, let's take a look at this one. This is the beauty of valence bond theory, because you can do kind of big molecules and it's not so difficult. And so let's look at that one first, the ClSOCl. Like this. Here, this is not a peroxide link. An OO bond is bad, but an OS should be okay. What's the hybridization on these? Well, what's the hybridization on chlorine? sp3, oxygen. 1, 2, 3, 4. Sulfur. They're all sp3. And so we could do the full analysis, but you know what? I'm not going to do the full analysis. I'm just going to draw this out. Because if chlorine is sp3, the way we draw that is 2 in the plane like this, and 1 coming out, 1 going in. And these are going to have lone pairs here. And this is going to bond here, right? This chlorine bonds to oxygen. Oxygen happens to be what? Hybridization as well. sp3. The way we're going to draw oxygen is like this. We'll draw 1 in the plane. Now when we overlap these, they have to overlap head on like this. And the second one in the plane is going to go up. And so that means 1 is coming down and out and 1 is coming down and in. These 2 will have a lone pair. So we should go with it. That. And then this will be a single electron here. We'll just put oxygen to spin down. And then comes sulfur. Sulfur is sp3 as well. We'll have sulfur spin down. And so we'll put 2 in the plane like this, 1 coming out, 1 going in. These will have 2 lone pairs here. This will have a single. We'll put sulfur as spin up. Sorry, spin up. And then we have a chlorine here. Like this. Should be spin down. 3 lone pairs. And so all we see are sp3 sigma bonds. There's free rotation here. And so right now we have a zigzag pattern, but that can rotate and flop around. When we draw structures like this, we draw it like this here. Chlorine, this would be a 3D. And so we put a lone pair in this bond in the plane, and then we have one lone pair sticking out. So we'll make bold, and one lone pair sticking in. We'll make dash. Okay, this is going to go to oxygen, and then it's going to go to sulfur, and then it's going to go to chlorine. And so do you see this zigzag pattern? This is typically the way we draw these sp3 chains. And so one lone pair coming out here on oxygen, one lone pair going in, one lone pair coming out on sulfur, one lone pair going in. Everything else is in the plane. Try to keep as much in the plane as possible. So we'll have one lone pair in the plane, one lone pair coming out, one lone pair going in. So sp3. Carbon likes to form these sp3 sigma bonds, so we form these chains, zigzag chains of carbon atoms. This. So this first structure is not bad, and then we can come up with the energy level diagrams that we did. But this second structure is the one we'll want to focus on. This one, because what is the hybridization on this? Sulfur here. Well, I have two choices. You know, this is what we call an expanded octet. I would label this series 2. Series 1 is going to be the one with what we call an octet. But the problem with this one is the formal charge. Sulfur is going to be short an electron, oxygen has an extra electron. Normally we try to minimize the formal charge by expanding the octet and forming multiple bonds. Sulfur is capable of doing this, right? For sulfur, we can expand the octet and form multiple bonds. But let's do the analysis for both structures. What people are finding out is that it's kind of a mix, you know? This shows some ionic character in the bond. Because the ionic character would just be opposite ions attracting each other. In this case, oxygen's negative, sulfur's positive. Versus a pi bonding character here. The actual is some kind of mix, often, of the two. Okay, so analyzing structure 1, what is the hybridization on sulfur? Sulfur is what? sp2? sp3, yeah. So we do have purple here. Sulfur is sp3. Oxygen? Oxygen is sp3. Chlorine? sp3, chlorine, sp3. Oh, they're all sp3. Let's take a look at sulfur first. We got 4 sp3 orbitals. How do I fill them for sulfur? Well, I see, what do you see on sulfur? I see one lone pair. It's going to be a lone pair. And 3 bonds. How many electrons does sulfur have? Normally sulfur has 6 electrons. In this structure, how many electrons does sulfur have? 5. And it's got a positive formal charge. It's got 1, 2, 3, 4, 5 electrons. And that's what we have here for sulfur, 5 electrons. And then we'll just bond the things. What's bonding to sulfur? Well, in oxygen, sp3 is bonding to sulfur. So that's going to come in here and bond here. Right? And then we have 2 chlorines. A chlorine sp3 here coming in, bond here, and another chlorine sp3 coming in, bond here. And so those are our bonds. And so we do this, we just draw out the sulfur, we draw out the 4 sp3 orbitals, always the same. 2 in the plane, 1 coming out, 1 going in. And then how should we do this? Well, let's put the lone pair up here. And then we'll bond the oxygen. Let's flip the oxygen down here. So I'm going to bond the oxygen down here. The oxygen's sp3 as well, so 2 in the plane, 1 coming out, 1 going in. Oxygen has 3 lone pairs, so we'll put them in here in 1 bond. So we got the sp3 sigma here. sp3. This is sigma bond here. And then we have 2 chlorines, and the chlorines are going to be like the last scenario. I'll try to draw it the best I can, but it's tough. And so chlorine's going to bond here and has 3 lone pairs. And 1 more chlorine is back here. This chlorine back here, you know, it's too hard to draw it in perspective. And so I'm just going to draw the 4 sp3 orbitals on chlorine the best I can here. And not worry about it too much. 3 lone pairs. Okay, all sp3 sigmas. Okay, this is going to result in a positive charge on the sulfur and a negative charge. These are real charges.
Does it matter if you put the lone pair of sulfur in the back and you put the...
No, it doesn't matter, but the reason I drew it like this is so we could see the trigonal pyramidal shape of this. This should be trigonal pyramidal molecular geometry, tetrahedral group geometry. When I draw this out, 3D, you know, it's going to look like this. Sulfur with lone pair in the plane, bonded in oxygen, put in the plane like this. Chlorine, another chlorine. These lone pairs I could try to draw in perspective, you know, but sometimes I make people do that. Like 1 lone pair in the plane, 1 lone pair comes out of the plane, 1 lone pair goes in. You know, something like that. But I don't know if I should. Because you're going to draw it like this anyway. It's really not necessary. And so this is where we have an sp3 sigma, and then there's going to be some ionic attraction. Do you see the ionic attraction because of the ion? But creating these ions is tough because that means, you know, one species gets oxidized 1 electron, the other species gains the electron. That costs energy, remember? Because we've got to deal with I1. Although we get a little bit of energy back from EA1, electron affinity 1. Versus doing this, you know, a lot of people say we want to get rid of the formal charge, and so one way of getting rid of that formal charge is to form a multiple bond and expand the octet on sulfur. But at what cost? At what cost is the expansion of the octet of sulfur? And so let's take a look at this. Sulfur, what's the hybridization here on sulfur? In structure 2. A lot of people say sp3D because they count this twice, but can you break up a double into 2 singles? You can't do that, and so that has to be treated as 1 group. And so we got a double bond group, a lone pair, 2 single bonds, so a total of 4 groups. A total of 4 groups means sp3 hybridized. It's sp3. sulfur is in period 3, and so when I look at these, I don't usually number them, but in this case I'm going to number them because we need it numbered. And so we're going to have 4 sp3 orbitals, and those come from period 3. Okay, how many electrons does sulfur have in this structure? Well, let's take a look at that. It has 1 lone pair. Do you see that? So we'll throw a lone pair in here. And then this sulfur has 1, 2, 3, 4, 5, 6 electrons. And so let's fill in the rest. 1, 2, 3, 4, 5. Where should I put the 6th electron? Where can I put the 6th electron? I have 5 electrons there. I'd like to do this. 6th electron. But I can't do that. Why? I can't do that because if I did the 6th electron like that, that means there are 2 lone pairs on sulfur. Are there 2 lone pairs on sulfur? No. I'd like to do this then. I'd like to put it in a p. But are there 4 p orbitals or only 3 p orbitals? There are only 3, plus 1, 0, and minus 1. There's no 4th p orbital. I'd like to throw it in the 4s, but the 4s are too far away. Right? And so what's next? The 3d. And so if this 6th electron goes into the 3d, which it does, it's going to skip the 4s and go right to the 3d because of n. Then shouldn't this be sp3d hybrid? No, this is not sp3d hybrid. This is not. Why is it not sp3d? Because sp3d. This is not sp3d because what I have is I have sp3 hybrid orbitals, and I'm using 1 unhybridized d orbital, and this is going to remain unhybridized. And so what I have here is this. I have a case of a PD pi bond. Let me show you what a PD pi bond looks like before drawing it on this structure. A p orbital looks like this. What does a d orbital look like? A d orbital looks like a 4-leaf clover. And so if I have a p orbital like this and a d orbital like this, take a look. They can overlap like this, right, as I bring them in closer together. And so this is called a PD pi bond. This is 1 bond, a PD pi bond. This is what I call the side view. What would the top view of something like this look like? The top view is hard to see, but you know, here we have a p orbital here, and then we're going to have a d orbital. 1 lobe coming out like this, another lobe coming out like this, and then 1 lobe coming in, and 1 lobe coming in. And so this would be the top view of a PD pi bond. All right, and so let's go ahead and figure this one out now. So the sulfur is going to be sp3 hybrid, so sp3 orbitals will just draw in like this. And so here are my 4 sp3 orbitals. And then let's take a look at the bond to the oxygen first. The bond to the oxygen is a double bond. And so the oxygen is, what's the hybridization on oxygen? The hybridization on oxygen is sp2. And so sp2 will have something like this, you know, 3 sp2 orbitals. 2 of these are going to have a lone pair. One of them is going to bond the sulfur here. And so the first bond I see is an sp3 sigma. sp3 sigma bond there. Now there's going to be, on oxygen, we saw oxygen before. This is sulfur. On oxygen, it's sp2 hybridization, which leaves one unhybridized p orbital. We got the two lone pairs here, and the orbitals like this. I'll put them spin down. And so basically what's happening is sulfur is coming in and bonding an sp3 here. So sulfur is going to bond sp3, and so we'll have no electron there. When I look at it from sulfur's perspective, an oxygen comes in here and bonds an sp2 right here, like that. Now, oxygen is going to have a p orbital here with one electron like this. I'll put it spin down. But sulfur also has a d orbital. And the d orbital we're going to look at top view. There's going to be a d orbital here. One lobe coming out like this. One lobe coming out like this. One lobe going in. One lobe going in. And so the four lobes, one orbital. This is going to have one electron here. And so this is my d orbital here. And so what results here is this. I'm going to get overlap here and here. And so this is going to be a PD pi bond. All right, and then on sulfur I also have two chlorines and a lone pair. And so the two chlorines I could put anywhere. You know, maybe I'll put the two chlorines here and I'll put the lone pair in the plane. So the chlorine comes here, bonds here. This chlorine is going to be tetrahedral as well. Three lone pairs. And so we'll have an sp3 sigma, and then another chlorine back here. It's all dashed. I'm going to make it because it's going in. And this is going to be sp3 sigma. And so that's the structure. This is what we're going to call the top view. And what we're going to do is we're going to rotate the structure here and get the side view. But before I do that, let's finish this. So sulfur is going to bond here with a d orbital to phosphorus's, oxygen's p orbital. Right here. And so this single sulfur bonds in two places, an sp3, sp2 sigma and a dp pi. That's on oxygen's energy level diagram. On sulfur's energy level diagram, we see this. The oxygen comes here, sp2, sp3 sigma, and a p orbital on oxygen is going to bond to a d orbital on sulfur. And so here's our double bond here. Here's our double bond here. This is the double bond looking from oxygen's point of view. This is the double bond looking from sulfur's point of view. All right, now let's rotate that structure and see the side view of that bond I'm trying to make here. And so what I'm going to do is I'm going to rotate the oxygen so that the p orbital is in profile. And you know what? I'm going to ignore all the other ones. Let's just look at the pi bond only. And so I have the p orbital here, and then I'm going to rotate the sulfur and throw the d orbital into perspective. And so here's the d orbital on sulfur. This sulfur is one orbital, it has one electron. This oxygen is one orbital, it has one electron. I mean the p orbital here. And the orbital overlap is here. Just because it overlaps in two places doesn't mean it's two bonds. Two bonds would require two orbitals overlapping with two orbitals. This is one orbital overlapping with one orbital overlapping with one orbital. No matter how many places the orbitals overlap, is still just one bond. So this is a single p, d, pi bond. perspective. Okay, and then I'm not going to write all the other stuff. Or should I write the sigma? Do you want the sigma in there? Yeah? All right, let's do the sigma. And so we're going to have sp2, and then this is going to be sp3. So like sp2, sp3 sigma here. Then oxygen is going to have an sp2 coming out with a lone pair and sp2 sticking in with a lone pair. sp2, sp2. And so that's a trigonal planar arrangement that's tilted on its side. And then the sulfur, now how did we rotate this? We took this and rotated it like this, 90 degrees. So this is going to come straight out, and the others are going to come in. And so there's going to be sp3 that's coming straight out here, and then 2 that are going to be stuck back in, like this, on sulfur. One of these will have a lone pair. So this one coming straight out is going to be the lone pair here. And these ones that are going in will be bonded to chlorine out here. And so chlorine is getting confusing, so we're not going to really do chlorine in full 3D like that. We'll just draw 2 in the plane, 1 coming out, 1 going in. Same thing here, chlorine, 2 in the plane, 1 coming out, 1 going in. We have this. And so this shows some more of the bonding, but the most important thing on the side perspective is to see the DP pi bond. Okay? That. All right, what's next structure? Now, the problem is, which one is it? Is it structure 1 or structure 2? Is it structure 1 or structure 2? In other words, should we expand the octet or should we just leave it as an octet? All right, and the answer is it's more towards structure 2 in this particular case. In that there is some PD pi bonding here, but we're going to come up with this general rule. To make one PD pi bond is not too difficult, but to make more than one is getting difficult. It's getting difficult because, do you know what orientation the d orbitals are to one another? The d orbitals are typically at 90-degree angles to one another. How many bond angles have you seen at 90 degrees? Not many. And so to get the angles, to minimize the repulsions, you know, we have to do a different kind of hybridization mix. And so things get more complicated. And so really what it is you take structure 1 and structure 2, and then you do a weighted hybrid of hybrids. Does that make sense? In other words, you mix them in appropriate amounts. What's the next one? Actually, we'll take a break, but what's the next one?
Nitrate.
Nitrate? We're going to skip nitrate because nitrate's straightforward. We're going to go to which one? Nitric acid is straightforward. Well, it's straightforward after I talk about resonance. And then what? Did you do chlorate? Did you have chlorate, ClO3 minus?
There's perchlorate.
Oh, perchlorate? Did you do perchlorate? Actually, is it perchlorate in the lab?
Yeah.
Okay, we did perchlorate. How many structures did we generate? A lot. Okay, we're going to do perchlorate next, which is going to be much more this is probably the most complicated one. And so we'll do perchlorate after our break. And then I'm going to set you guys off on your own.